In this video, we're going to look at molecular dipole moments. To consider molecular dipole moments, we first have to consider bond dipole moments. To do that, let's consider a simple biatomic molecule, hydrogen chloride. To calculate the bond dipole moment, we have to consider the differences in electronegativity between the two atoms in a covalent bond. Here we have hydrogen and chlorine. From the periodic trends, we know that chlorine is much more electronegative than hydrogen. So if we go to draw in our bond dipole, we can see that the electron density is going to be pulled towards the chlorine, which is going to give us a bond dipole along the bond towards chlorine. We can also determine from this that we're going to have a partial positive charge on our hydrogen and a partial negative charge on the chlorine. This is our bond dipole. It also happens to be our molecular dipole. Since this is the only dipole in the molecule, the molecular dipole would also be in the same direction. When we consider the dipole moment of a molecule, we have to consider what a dipole moment is portraying. A dipole moment can be considered mathematically as vectors with a magnitude and direction. If we think about that, then the molecular dipole moment is therefore the sum of the vectors. Let's look at a simple problem. If I had a very large magnitude vector in one direction and two smaller magnitude vectors in other directions, when I sum those, the overall would be a smaller vector going in the direction of the larger magnitude. It's a little simpler to actually just look at some molecules and figure out the molecular dipole moments. So let's go ahead and move to some examples. So let's look at carbon dioxide. The first step we need to do is look at carbon dioxide and figure out the molecular geometry. We do this by knowing the Lewis structure. So if we draw the Lewis structure, we see that the carbon's in the middle, double bonded oxygens on both sides, and then lone pairs on the oxygens. Since this is just one central atom with two atoms attached, this is going to be linear. So this is also our molecular geometry. Now let's figure out our bond dipoles. Consider your periodic trends. Which of the atoms is more electronegative? Well, from the periodic table, we know that oxygen is more electronegative than the carbon. So therefore, we can draw our bond dipoles in the direction of the oxygens. Now let's consider vector sum. Since both vectors are the same, carbon to oxygen, and they're 180 degrees deposed, therefore we know that the addition of those two vectors would actually be 0. So therefore, my molecular dipole would be 0. Let's try another one. H2O, water. Again, we need to know the molecular geometry. We can do that by first showing the Lewis structure. There is a Lewis structure for water, but is that the correct geometry? Well, if we consider that, that's 4 electron groups of one central atom. Well, 4 electron groups is not going to be square planar, it's going to be tetrahedral. And if we consider the repulsion forces, the lone pairs are going to repulse greater than the hydrogen. And so therefore we can draw this molecular geometry in this fashion, here showing the two hydrogens going down and our lone pairs going up, one of them coming at us and one of them going away. Then we need to consider the bond dipoles. Which atom is going to be more electronegative? Again, look at your periodic trends. Oxygen is more electronegative than hydrogen. So therefore, we're going to have the bond dipole moments going towards the oxygen. If we think about vectors, if we have both of those going towards the oxygen, what is the sum of those? And what we see is a molecular dipole going towards oxygen. So as long as we can get the correct molecular geometry, figure out our bond dipoles, and then consider the summation of those vectors from the dipoles, we can come up with our molecular dipole. Let's look at a couple more examples. Chloroform. If we look at chloroform, we can draw the Lewis structure. Consider Lewis structure. This is like water because we have 4 electron groups. So therefore, if we convert this to a molecular geometry, we should end up with something that's tetrahedral. Here we have all 4 atoms. So therefore, the AXE, X is going to be 4. So therefore, we do have a tetrahedral. I'm going to show the hydrogen going up. Chlorine. Then again, remember we show 3-dimensional by the wedge and the dash. So here we have my chloroform in its molecular geometry. If I put in my bond dipole moments, we'll see that the chlorine from the periodic trends is more electronegative than the carbon. we end up with these three bond dipoles towards chlorine. If we consider carbon to hydrogen, this is often considered not to have a bond dipole, but if we do have to consider a bond dipole, we would say that there's a small bond dipole going towards carbon. So if we consider that, we would have a small bond dipole between hydrogen and carbon. We do the summation of those to end up with our molecular. We see that the three chlorines are going down, and so we get a molecular dipole going in the direction of the chlorine. One more example. Let's look at carbon tetrachloride. Here again, let's go ahead and just go straight to the molecular geometry. It's got 4 atoms around one central, so that's going to be a tetrahedral. If we think about our bond dipoles, again from periodic trends, chlorine is more electronegative than carbon, so we can put in our bond dipoles. If we look at the molecular dipole, again we need to look at all of those bond dipoles. They're all pulling at the same magnitude at 109.5 degrees away from the central atom. So therefore, what is going to be the molecular dipole? That's correct. Molecular dipole is going to be 0. All the vectors will cancel. Practice determining molecular dipole moments. They're not difficult as long as you consider the electronegativities and the correct molecular geometries. Practice and become confident.